the announcements here because one of these is important. I want everybody to have an opportunity to hear it, though there's not a lot of time, but there is time for it. Have y'all heard about these informational sessions that are going on concerning institutional scholarships and summer Pell? These are happening tomorrow. 2 on this campus, 2 on the Birmingham West campus. The 2 on this campus are, well, all of them are 11 to 1 tomorrow over the noon hour, and then another one 5 to 6:30 in the evening. So on both campuses, they're held at the same time. The one on this campus is in the faculty staff dining room. Now, to let you know where this is, and by the way, I don't know if any faculty or staff that even use that from the old days, is the faculty staff dining room. You go out the door here, and then go 2/3 of the way down this long hallway, past the first stairwell. When you get to the second stairwell, stop, take a left, go down half a flight. Okay, some of you are doing the labs on that stairwell. Take half a flight, and then go straight down that hall in front of you. You have to make a little jig to the right and then to the left. There's the faculty dining room right before you get to the cafeteria. That's it right there. Good sized space. In the old days, a little bit of history here. When I first started working here, we were Western State Technical College. And we had on swipe badges that we had to swipe in and out every time we came on campus and left campus. And we had to record our hours by the swipes, you know. So therefore, no one went off campus for lunch. I mean, no instructors. Students could, no sweat. But instructors and staff, we could not unless we made up the hours later. So therefore, we all ate in the cafeteria pretty much, and that was a pretty popular place, and there was always people eating lunch there. Nowadays, after we merged with Lawson, they did away with that, so there's really people either eat in the office, eat off campus, or whatever, because we don't have the swipe cards anymore. So the likelihood of running into anybody over the noon hour, not very likely. You have the room to yourself. Now, what are these informational sessions about? About 7 or 8 years ago, I think it was, they expanded Pell Grants, and if you registered for them in the spring, which is when they want you to, okay, and then you went to, if you got all the paperwork in and everything done, they tried this for a couple of summers, let people use the Pell money in the summer too. Boy, was it ever popular here. We had record attendance a summer or two there, or at least for me it was, and it was really nice. And then I think midterm elections came and they cut it. I don't know if that's why, but it was cut. And we haven't had them for several years now, and now they're putting them back in. That's really good. Now, before they had that, and since in between, the college has always done all they could to get scholarship money for the summer, because Pell Grant usually would just cover for full-time students fall and spring. And usually there'd be no money or very little money left over for summer. If you're a part-time student, you may have money left over for summer, but full-time students usually didn't. So the college tried to get scholarship money every place it could, the foundation and other places. And we were able to very competitively, provide a few courses for a few students, maybe only one course for a student or something like that. And so anyway, we have the scholarship money. Well, now that Pell is doing this again, having summer Pell, I see it on the screens and stuff here, those monies are freed up. So if you are a Pell student and you will be here in the summer, I know most of you will not, or you're hoping not to, but if you will be here in the summer, if you got your Pell done, you can use Pell dollars for the summer, which means that's going to free up a bunch of scholarship money, okay? So those of you who don't qualify for Pell, you may be able to get some scholarship money this summer. So take advantage of it, and that's what these sessions are about. Tomorrow from 11 to 1 and 5 to 6:30, 2 meetings in the faculty staff dining room. Now, if you happen to be on the Birmingham campus tomorrow at either of those times, they're meeting in the on the West Campus, the Leon Kennedy Center, which is also often called the Student Center, and the cafeteria, which I found pretty interesting because 11 to 1 is the biggest time for people to be eating in the cafeteria, and I guess it's a big enough room they can have the meeting down on one end and the people around. 5 to 6:30, even the residence hall people will be eating, but that's a much smaller crowd, so I'm sure they'll have plenty of room then. But I would think the biggest crowd for the meetings would be 11 to 1, so that'll be interesting. But anyway, these are sponsored by Office of Student Financial Services. Please go. If you want to be here in the summer, but you can't afford it, either get your Pell lined up so you can be here, or check into those institutional scholarships. Now, the reason they're having the thing now, usually those institutional scholarships, the deadline is around April the 15th. They'll be telling you this at the meeting, so they'll tell you everything you need to do to get moving along on that in time to get them in. If any of you are interested in the math team, Mr. Rossi meets with them Fridays at noon and Mondays at 3 in the Birmingham West Campus Science Building, which is the C Hall C100. And then tutoring, we have tutoring available and positions for you to tutor if you're good at any of the subjects. That free tutoring is available on this campus. If you go down the same hallway here, go to that same door, the second stairwell, don't go to the left, head to the right. That's the tutoring lab, okay? You can get tutoring just about any subject there. Now, if no one's in there, the woman who used to have an office in there moved on to another job, not on campus anymore, not at Lawson anymore, so they haven't replaced her yet. So if no one's in there for you to contact, go on to the end of the hall, hang a left, the last office on the right before you get to the restrooms, that's Student Support Services. They can help you, either if you need tutoring or you want to become a tutor. That's Student Support Services tutoring. Space Center, go down to the same hall, to that same second stairwell, but rather than going to the right, go down the stairwell one complete flight, not just to the middle level, but to the bottom level. And there, when you hook around the corner, the Space Center is right there. You'll see a big sign there. And that's where you can either get tutoring or sign up to tutor. If you have made an A or B in any subject, I think you're qualified to tutor in that subject. And this is Alexis. Okay. Anyone else come in since I called roll? Okay, it looks like we're only missing now Gary, Coco, and Courtney. Okay, good deal. All right. Any questions on anything we've done up till now? Hope you had a good spring break, and I'm sure y'all are just holding off the papers until a little bit later, turning in all the papers you worked on and finished over spring break. But I'll take them anytime, okay? Or if you're needing the proof just a little bit more, get those into me, okay? Sooner rather than later. Okay, good deal. Now, oh, you got it? Oh, wow. Okay,
how many points is that, David?
More labs. Good. All right. Okay. Thank you. Anyone else? Just when I get all the labs great or things graded, here comes more. Okay, story of my life. All right, any more questions? All right, now last time we got through, we were just beginning to talk about motion, position, and energy. Now, I was thinking we'd already done this, but I guess not. See, I'm teaching a physics class, and we're going over the same stuff. I thought we had already hit this. We'll start with potential energy. There are tons of different types of potential energy, okay? The main one we're going to look at now is gravitational potential energy, but there are plenty of others. Spring potential energy, chemical potential energy, electrical potential energy. There are lots of potential energies out there. We're going to talk about mostly gravitational potential energy. And this is the energy associated with position. Now, all all of those sort of do, but this is more so. Gravitational potential energy. And what you have to do with it, the very first thing, is to establish your reference level. Okay? I can hold this book up here. Okay? Now, I've added work to it to get it up there, so I've been adding potential energy to it, gravitational potential energy, because as soon as I release it, it's going to fall straight down toward the center of the earth, right? So that's going to be, I've added gravitational potential energy to it. How much? Well, it depends on where you want to take as your reference. Since I picked it up from the desktop could be how much I added. But if I'm going to drop it on the floor, I may want the floor to be my reference level. But if I were to walk over here to the window and hold it out the window, I might want the ground to be the reference level. Or, if I was up in an aircraft plane over the Gulf of Mexico, I may want the surface of the earth to be the reference. You get to choose what the reference level is. And what I like to suggest is use the position that's as low as the object can go in the context of your experiment or observation. So you determine the reference level, and then you measure the height above that reference level, above the desk, above the floor, above the ground, above sea level, whatever you're using as your reference height. When we do the lab today, the floor, no. The lowest point that the material can go, that will be our reference level. So the first thing we do will be measuring that distance from the floor. Now there's also other types of potential energy. Elastic potential energy, which would be spring potential energy. Okay? You know about those from the springs in a car. Okay? A slinky, any kind of spring closing the door, any type of that, like a spring like that. Also, in some senses, a shock absorber sort of acts like that, but not quite the same. Electrical potential energy, which we'll cover in 2 chapters, okay? That is charges. And again, it's position of the charges, so that's another type. Chemical potential energy, just all kinds of different potential energies. Work can change the potential energy. Like I just said, lifting the book is adding potential energy to the book, okay? Work can change the potential energy. Kinetic energy, which we'll study next, is the energy not of position, but the energy of motion. Okay? Kinetic means moving. Okay? So kinetic energy can also change into potential energy. Okay? I throw a ball upward. Okay? As the ball is going up, it's losing speed, which is your velocity, which is the energy of motion, and gaining potential energy as it goes. And somewhere up there, the ball stops. Now, it's all the energy it has is potential energy, no more kinetic energy because it's not moving anymore. But that's only for an instant, because then it starts coming back down again, and as it comes back down, it loses potential energy and gains kinetic energy. So kinetic energy can change into potential energy and vice versa. All right, here's Coco. Now I've just got to find you. There you are. All right. Anyone else come in since I called roll? Okay. Any questions so far about potential energy? All right, here we have a book being held on the 4th story of a building. Above the floor there, if you use that to be your reference position, then and here's the formula for gravitational potential energy. Because there's so many kinds of potential energy, I like to call this GPE. Not just potential energy, but GPE. The other book I teach from just calls it E sub P, potential energy. Well, if it's gravitational, I think you need to have the G in there. So in the lab and other places, you'll see I usually put, let me get my pen adjusted. I usually call this gravitational potential energy. And I'm sorry?
Can I go somewhere and take my test that I missed Thursday?
Well, can you do it later? because I think we'll finish lab early today.
Okay.
It's a very short lab.
Okay. Can I have the lab from Thursday?
Yeah, you going to work on it now?
No, I just.
Okay, well, let me give it to you when I pass out the labs, because I have to go through and find it all.
Okay.
Yeah, okay. Okay, you could measure this, and what I was going to say, the reason it's gravitational potential energy, look what's in the formula. The acceleration due to gravity. The formula for gravitational potential energy is mgh, where m is the mass of the book, g is the acceleration due to gravity, which is, say again?
Motion.
What value? 9.80 or 9.8. What units? Meters. Say again? Per second squared. That's an acceleration. And h is the height. So if this is your zero reference level, that's your height. Okay? Now, if you move to the wind that dropped it out, but kept that same reference position, at this, your height is zero, your gravitational potential energy is zero. Up here, it would be a positive gravitational potential energy. If you went to the window, keeping the floor on the third story, fourth floor, as your reference level, went to the window and dropped the book, and went all the way down here, then it would be minus potential energy, because there's your zero level. Zero reference position is right there. Then you would have a negative potential energy. Now, I don't like the way they phrase this, because this H and that H are not the same. This is that H. This would be this H. In fact, it's the negative H. It would be mg times the negative H. How far down you are from the thing. So potential energy could be positive. It could be zero. It could be negative, depending on where you set the reference level. What we're usually interested in is not the value of the potential energy, but the change in potential energy. And that's going to be positive if you're adding energy to it going up, negative if you're going down. So that's why this turned out being negative potential energy here. If we had chosen this to be our zero reference level to begin with, then this would have been that H, this H, and here it would have been zero. So you get to choose your zero reference level, and then your potential energy, and I like to call it gravitational potential energy, is based on that, but what we're interested in is the change. And wherever you set it, the change will be pretty much the same. All right. I think we're about ready. Yes, we are ready for example 3.5 and 6. Okay? Now, let me point out a couple more things. Okay. Goodness gracious. Okay. Just a couple of things to note here. Here's the formula for gravitational potential energy, right? mgh. You'll use this today in lab, okay? What is mg, by the way? M is mass. What's mg together? Well, g is acceleration due to gravity. What's mg together? Step on the scale, I'm measuring weight. mg is weight, right? mg is your weight. So if you're using the U.S. customary, we don't use mass then. We use pounds, which measures weight, so it'd just be weight times height. So whichever we do. Remember in the lab you did last Thursday, okay? Remember your force was your weight, okay? Because we were using pounds in that lab, okay? So just to point that out to you. Let's move, okay, back here. All right, example 3.5. What is the potential energy of a 2.14 kilogram book? 2.14 kilogram. What's that a measure of? That's your mass, the mass of the book. Okay? That is on a bookshelf 1 meter above the floor. What would that be a measure of? That's your height. That's what this formula uses too. So what is the gravitational potential energy of that book relative to the floor? GPE, I can't write. GPE, what's the formula for it? mgh. So what is gravitational potential energy relative to the floor? 2.14 kilograms times 9.8. What units? Meters per second squared times 1.0 meters. Sure isn't adding much value, but it is adding a unit, which is important. And what's that gravitational potential energy? I don't have a calculator on me. It's going to be something around 20, isn't it? What you got? Anyone got a calculator? Say again. 20.972. What units? Kilogram, meters squared per second squared. And what is that also known as?
It's also known as,
A Newton is a kilogram meter per second squared. That's a Newton.
Can't you do the square thing?
Okay, you could express this as a Newton meter because it's kilogram meter per second squared times a meter. That would be a Newton meter, but that also has a name. A what? A joule, exactly. Okay, so there's your joule. And remember, potential energy is measured in joules, work's measured in joules, all energy is measured in joules. There's your... Now, to satisfy the significant digits, what would you probably round that to?
21.
21, exactly. Because you have 3 significant digits for your mass, only 2 for the height, 2 for the acceleration due to gravity, so you would write this as about 21 joules. Okay? Your calculator may give you all those digits, but that would be 21 joules, and that's what they got in the book. Okay? So let's clear. Anyone need that a little longer? Everybody got it? Okay, let's do example 3.6. How much work can a 5 kilogram mass, 5.00 kilograms, and they already told you that's your mass, okay, do if it is 5.00 meters above the ground? What's that a measure of? The height, okay? Now, what do we mean by that? If I were holding 5.00 kilograms, 5.00 meters, I'd have to be up on something because I can't reach that high. I'm about 2 meters high. The ceiling's about 3. You have to be another 2 meters above that. So I was standing on the floor above this, dropping it through a hole. That'd be 5 meters. 5 kilograms is a pretty reasonable thing. That'd be about 4 or 5 of these books, okay? How much work could it do on your toe? I mean, on your, something if I dropped it there. It's going to be significant if it's your toe, okay? How do we calculate that? How do we calculate it? Say again? We use the same thing because you're changing its potential energy from the maximum to 0 at this reference level. So how much work can it do? That amount of energy. So what would that be? Yes, that would be mgh. So the work done, capital W is work, is mgh also. Force times the distance. The force is your weight times the distance, and that would be 5.00 kilograms times
5.00
Okay, 9.8 meters per second squared times 5.00 meters. Okay, now that's going to be about 240 some, right? They round to 250. I guess it might. What do you get on your calculator? 245 joules. Kilogram meter squared per second squared is a joule. What they did, because this only has two significant digits, they round that to 250, which is, I think 245 is closer to what it really is, but with only two significant digits, they rounded to 250. Sort of a stretch. That introduces some round-off error there, so don't use that in the middle of the problem. Carry all your digits with you until you get to the end. Okay. Now, the concepts applied you see on page 69 is basically the lab we did last time. Okay. Now, I also want to mention this. I probably mentioned it before, but I'm going to say it again. I've noticed, especially when I've taught classes, which I do fall and spring, that have mostly automotive students in it, y'all use energy, power, all these terms almost as if they're meaning the same thing, right? They don't, okay? So that little blurb there on work and power, you just need to realize those are two completely different words. They're related, but they're not the same, okay? Power is the rate at which you do work, and energy and work, those are the same units, okay? So let's move on to kinetic energy. What is kinetic energy?
Energy associated.
All right, reads well. Energy associated with motion as opposed to potential is?
Energy associated with height.
Or position, exactly, okay? So this is kinetic energy, the energy associated with motion. It results either from work or change of potential energy. Now, if I had a baseball here and I threw it really hard to Will back there, I'd break his phone, but you know, that's all right. I wouldn't mind doing that. Okay? When I gave that energy, did work on the ball, and gave it that energy to make it move, that's kinetic energy resulting from work. I did work on the ball, increased its speed, and gave it that energy. That's kinetic energy. Or if someone climbed up into the ceiling above here, up on the rooftop, and dropped that 5 meters onto Will's phone, then they also would be doing work on it. That would be change of potential energy resulting in kinetic energy. Okay. Now, they have this, but they need something before that. Here is the formula for kinetic energy. Okay? 1/2 mv squared. The m standing for mass, and the v standing for velocity, motion, velocity. That's where the velocity comes from. There's no g in here, so it's not by gravity. There's no h in here, so it's not by position. This is the mass is still in there, but the velocity is associated with motion. Okay? Now, can you pick out a few things that are similar and different between potential energy, gravitational potential energy, and kinetic energy? I've already mentioned a couple. Differences are that gravitational potential energy depends on position, your height, right? This depends on speed or velocity. Okay. Now, the difference is for the gravitational potential energy, the height was to the first power, the velocity or the speed is to the second power. So it's proportional to the speed squared, not the speed to the first power. Okay? Now, kind of a result of that, remember we said gravitational potential energy can be positive, 0, or negative. How about kinetic energy? It cannot be negative, because whatever your speed is, whether you're going forwards or backwards, square that and guess what it is? Positive. Your mass is never negative. You can't have a negative mass, okay? And 1/2 is just a positive 1/2. So this can never, ever, ever be negative, okay? Now, notice something else here, though. Going back to the square of the speed. When you double the speed, so the first time you did it was v, that's 1/2 mv squared. When you double the speed, it's 1/2 m2v squared. And when you double that, it's 4 times the kinetic energy you had before. Now, what's the ramification of that? It has something to do with tailgating. When you are traveling down the road, city street, maybe 25 miles per hour, and you're going to have to come to a stop, okay? It's going to take you a certain distance, right? That depends on you're changing your kinetic energy, and it's going to take you a certain distance to do that. Now you're driving down the highway at 50 miles per hour, double the speed. What would be your distance to stop? Say again? 4 times. 4 times. You're driving down the interstate at 75 miles per hour, and I won't tell them that you're going that fast, okay? Okay? And you're doing that, how far will it take you to stop compared to the 25? Say again? 6 times. Square. 3 times square. 9 times the distance. So, will you follow someone on the expressway at the same distance you would on the city street? You better not. Because if something happens suddenly, there's no way you're going to be able to stop in the same length of time, the same distance that you took on a city street. Double the speed, increase the kinetic energy by 4. That increases your impact on the steering column, on the windshield, or whatever, increases that by 4 times too. Okay? It's a pretty important concept to keep in mind. Okay? And I see just about every day driving to work these people, being nice now, that come up on people trying to get them to move. I mean, they get closer than I would on the city street, okay? Think, man, if something happens, where will I be? Where's the closest safe ditch to get to? Because it's going to be bad if something were to happen, but fortunately, so far it hasn't. Okay. Whoa. That's all we had on kinetic energy. I bet you we have a couple of examples to do, but before we do that, let's go back to that formula. What are the units for kinetic energy? What's the unit for mass, for 1/2? There is no unit. That's just a number, a pure number. How about mass? What's the unit for mass? Kilograms, okay? How about velocity? Second? What's the unit for velocity? Metric. SI unit. Meters per second. But you're going to square that, and that gives you meters squared per second squared times kilogram. Kilogram, meters squared per second squared. Sure enough, that is a joule. So this energy is the same as work. It's the same as potential energy. All the units are the same. Okay? So let's do kinetic energy is measured in joules. Now, in the U.S. customary, remember it's foot-pounds. Okay, excuse me. All right. Let's do example 3.7. Okay? A 7-kilogram bowling ball. What's that a measure of? That's your mass of the bowling ball. Is moving in a bowling lane, good place for a bowling ball to be moving, with a velocity of, so they've already told you this is velocity of 5 meters per second. 5.00 meters per second. Okay. Now, notice here, I should have mentioned this before. I've even said it. The V here, really, since this isn't the vector V, it's not a bold V, it's not got an arrow over it, and in the book it's usually written in italics. That stands for speed now. It's really not velocity, it's speed, okay? And, you know, speed is the magnitude of the velocity anyway. But that really isn't velocity, it's speed. In the book they called it velocity, but it's speed. What is the kinetic energy of the ball? So what is the kinetic energy of that ball, that bowling ball? What's the formula? 1/2 m times v squared. Okay, so that'd be 1/2, and your mass was 7.00 kilograms, and then your velocity was, or speed was, see I said it too, 5.00, what units? Meter per second, but you're squaring the speed. So let's hit it again. That would be 1/2 of, not 35, but, okay, 7.00 kilograms times 25, and you could put 0.0 if you want to. What units? Meter squared per second squared, because you square the units as well as the number. And someone with a calculator, help me out here. I don't usually do that one in my head. Well, you can too. That would be 175, and half of that would be 87.5, what units? Joules. Kilogram meter squared per second squared is indeed a joule. So 87.5. And that's what we got in the book, good for them. See, all your significant digits are fine. Now, what if you had written this 1/2 as 0.5? Would that decrease your significant digits? No, 1/2 is 0.5000000, as many as you want. It's exactly that. So that wouldn't mess up there. Even if you only put 0.5, that's good forever. 0.50000. It's precise, exact. Okay. So let's move on to example 3.8. And I experienced this one, something fairly similar to it in my own life. A 100-kilogram football player. What's that a measure of? That's the mass of the football player. Okay. Now, by the way, just for your reference, that's about 220 pounds. Okay? Healthy guy. Okay? A 100-kilogram football player moving with a velocity of, or speed of, 6 meters per second. 6.0 meters per second. Okay? Tackles a stationary quarterback. Okay. Quarterback's not moving. That's what it sounds like certain defenses I know about. Okay? How much work was done on the quarterback? Now, the work would be change of kinetic energy. Okay? So what was his initial kinetic energy? What's the formula? Help me. It's been a while, hasn't it? At least 3 minutes, huh?
Oh my God.
Yes. 1/2 mv squared. Okay, that would be 1/2 of 100.0 kilograms times 6.0, what units? Meters per second squared. Okay? So this time I'm going to go and take half of 100 and make it 50.0 kilograms. Okay? Times, and then what's this? 36, what units? Meters squared per second squared. Okay. And that would be about 18,000? 1,800, I think it is, right? Yeah. That would be 1,800, what units? Joules. Okay. Whoa. Okay. Now that worked out pretty nice for us because really we only had two significant digits here. We only have two there, even though we're using all that we had. So 1,800 joules. Now I remember not quite the same setup, but something pretty close to it. When I was in high school, we went to a really small high school, so if anyone who went out for a sport could make the team no matter how poor you were at it. Because they just needed bodies. And it was when I was probably a freshman or sophomore, and I was on the B team, but we had to practice with the varsity because they didn't have enough. So when we ran a defense for the varsity offense, there we were. I was playing defensive end at the time, and a really good guard had pulled and had come to block me, and I was so fortunate. I just barely missed him. Wasn't usually that good. Just got him out of the way and looked up, and here came Bill Boyce. Now, Bill Boyce lived right up the road from us. We had a beef cattle farm and general grains and things like this. They had a dairy farm. So Bill was hardly ever drank water. He drank milk instead. So he was a pretty healthy guy. I mean, he was very close to, this back before players were as big as they are, but he was very close to 200 pounds. And I was probably sophomore year sitting around 170, 180, something like that. And just got Alvin Burke out of the way and looked up, and here came Bill full speed. And he had pretty good speed too. And I was dead still. Okay? All I had time to do was just wrap my hands around him as his knee pounded my chest and body to death. And I did get him down a few yards down the field. I did make the tackle, but it was not very pleasant. Okay, and it was pretty rugged. So I can relate to that quarterback having about 1,800 joules. Now Bill wasn't quite 220. Okay, a little bit less than that. He was probably going pretty close to 6 meters per second. I don't know that for sure, but it was not a pleasant experience. I got the tackle, but that was about it. Okay. Any questions on kinetic energy or potential energy? Okay. Now they're talking, and the slides here are a little bit, no, they're on track. I think a little bit later they're going to get a little out. Now we're going to talk about energy flow. Now that's an interesting phrase, energy flow. And it came from, I think, the old concept that heat was actually a material. A massless material, but something that was in the substance of an object. Okay? And since it was material, they talked about it flowing. Now, we aren't into heat yet. That's the next chapter, okay? But I think this concept of energy flowing comes from that. What they mean is energy, if you go back to probably the last slide we did before the break, you'll see that energy is the ability to do work, and work is the results from a change of energy, okay? So it seems like energy and work and things. It almost does seem like the flip. Energy can do work as work against inertia. Now, what do we mean by that? Say again? Okay, that would be work against friction. Okay, work against inertia. Say again? Rolling what? Chair. Okay, yeah. That was inertia. If I rolled the chair to you and you stopped it, you would be doing work against this inertia because its inertia had it moving. Or if I gave it a push and it was at rest, I'd do work against it. I give it kinetic energy. So I did work against the inertia. Okay? So that's work against inertia. They show here, I think, pushing a car. Okay? Certainly, I'm glad it's a Volkswagen, but it's to do work against that, the inertia wants it to remain at rest, okay? And you're trying to get it to move, okay? So that's work against inertia. Work against gravity, what would be an example of that? Say again? Something falling or lifting something. Yeah, either one. So this would be an example of work against gravity. Gravity is pulling downward, you're lifting it upward. That's work against gravity. Okay? Work against friction, you mentioned. Work against friction, the box is sitting on the floor. You're trying to move it this way. Friction is resisting. Friction always resists the direction of the motion. Okay? If you're pushing this way, it's going to be opposing you always. You pull this way, it's going that way. Really counting, okay? So that is work against friction. Now, what do we mean by work against shape? Anyone think of an example of that? Say again? Okay, now that's sort of this one, isn't it? Now, if you're bending the refrigerator as you're pushing, yeah, you're working against the shape. Hopefully you're not, if it's your refrigerator. Or even more so, if it's my refrigerator, I don't want you bending it. But you could make a dent in it. But something like that, if a car, you're working against the shape of the car. Okay? Now, again, I have a dumb example of this one. When I was in, actually, all the time I was in school, we had intramural teams. So, last bit that I did at UAB, but when I was a full-time student, I always did that. I just needed to burn off energy. Okay? And when I was in grad school at Nebraska, we were, a group of us got together in a co-ed volleyball team, okay, league. And have y'all played volleyball before? Those balls, they look like they might be soft. They really aren't. They have a lot of pressure in those balls, okay? They're hard. And I remember we were playing this other co-ed team, and we were watching them warm up as we were warming up. And they had this one gal, you can tell she had played some volleyball. That two, really. One was really tall, and you could just watch her, and she was a spiker, okay? She knew what she was doing. And there was other little gal on the team who just could set it perfectly. I mean, she was a setter. Now, they have other positions on volleyball teams. They have names for them. But these two, and sure enough, we knew, the teams rotate, around in volleyball. I knew at some point she'd be across from me, and she was, okay? And I don't know who served or what, probably we served to them. And someone got the ball, got it up in front of the setter. She had it perfectly in front of this spiker. And all I could do was go up and make as big an area as I could, hoping that when she came down with it, I could get it back down on the other side. So here it came, went up, and boy, she had trajectory downward on the thing because I was going up, and that ball didn't hit my hands at all, right in the face. And I felt at the same time that ball touched each ear. Okay? Now that was a hard, well pumped up volleyball, and it touched each ear with my face in between. Okay? I did some work against the shape. All I saw was Wilson, but it did I did work against that ball. And it fell down on my side of the net to boot. Okay. So that is my example of work against shape. Okay. The example they give may be a bit more reasonable, working against the spring. Either compressing the spring, it's pushing back, or stretching the spring, it's pulling back. You're doing work against the shape of the spring. Okay? And then you can have work against various combinations of these. Okay? Pushing a car and you actually push too hard and dent the trunk or something like that. That would be work against shape, work against inertia, and possibly work against friction if they had the brake on and you were pushing on it. Okay? Not a good idea. But that's how energy flows. You can work against all kinds of different forces here, and it is expending energy. Now they move on to energy forms here. And let's just talk about these in general. This one, the first one, you will be using in the lab today. What in the world do we mean by mechanical energy? Mechanical energy, the definition of it is the sum of the kinetic plus potential energy. Okay? And if you think about this, most of the early examples we did, you throw a ball into the air. You're working on the ball, giving it speed, giving it kinetic energy, but then the earth is pulling down on it, so once it leaves your hand, that's about the maximum speed it'll ever have, because as soon as it leaves your hand, the only force acting on it is gravity, which is decreasing its speed. So that would be changing, the kinetic energy is changing potential energy. As it goes up, it's losing kinetic, gaining potential. Until it reaches that highest point up there, when it reaches there, it's all potential energy, because it's no longer moving instantaneously. That moment that it stops, zero kinetic energy. But then what happens immediately? It starts coming down, losing potential energy, gaining kinetic energy, but the total mechanical energy of that is the sum of these two, and that's going to be constant throughout the motion of the ball, as long as you're neglecting air resistance. Okay? If you have any air resistance, then there is some loss there, but otherwise your mechanical energy is conserved. Okay? Another form of energy is electrical energy. And again, there's a potential here, and that's the potential between two charges. If they're like charges, they're repelling each other, and you have to do work to bring them together. If they're unlike charges, they're attracting each other, and you have to do work to keep them apart. But that's electrical energy. Charges, currents, that kind of stuff. We'll talk about that in 2 chapters. Chemical energy. Now, we're not going to have much time to talk about this. This will be chapter 8, the last chapter we do. And we won't get into that much on the energy side, but it's energy involved with chemical reactions. Any chemical reactions going on around here? What? Any of you eat lunch? Yeah, you're digesting your food. There's a chemical reaction. See the little green leaves on the trees out there? What are they doing? They're creating food. They're pulling carbon dioxide out of the air, water out of the ground, and combining carbon dioxide and water to form carbohydrates, simple sugars. Okay? Now, nothing on that tree probably tastes very sweet, but that's what it is. That's the energy that tree uses. It'll transfer that into cellulose, which is a complex carbohydrate. That's what makes the wood. Okay? So there are chemical energies going on all over the place there. Keep in mind, okay, now, where is it getting the energy to take carbon dioxide from the air, water from the ground, and making it? You have to be changing the energy of that carbon dioxide, water, and making it into a simple sugar. Where's it getting the energy to do that? The sun. The sun is supplying the energy because in those little green leaves, what makes them green? Chlorophyll, exactly. And that chlorophyll contains in it chemicals. Two of them happen to be ADP and ATP, adenosine triphosphate and adenosine biphosphate. And by jumping from one to another, it's exchanging energy. When that happens, and chlorophyll is making that happen, that's where they get the energy to combine carbon dioxide with the water and make carbohydrates. Later, you'll eat, if that was a fruit tree or something like that, eat the fruit or the nut or something that comes off that tree, and then your body converts that stored chemical energy into energy of motion, energy of whatever. Okay? So chemical energy involved with any time there's a chemical reaction. What are some chemical reactions going on in a car? Say again? Combustion is chemical energy. Where did the fuel get its energy? Actually, it came from the sun too, because you see those, we're going to get into this a little bit later, but the gasoline it came from stored carbohydrates that later became hydrocarbons that stayed in the earth for a long, long period of time being formed, and that's where we're converting some of those. So that energy also originally came from the sun. Okay? Chemical reactions. Okay? When you go to start your car, you're not combusting yet. What chemical energy are you using there? The battery. Okay? There you have electrical energy, stored electrical energy. You have lead sulfate and lead plates in the battery. I think that's what they are nowadays, or it used to be anyway. And there's a potential difference between them, and that's what's supplying the energy to get the starter to turn, to get the combustion process to start, and to provide the sparks to the spark plugs, okay, or whatever you're using. Okay? Again, chemical energy there. Radiant energy, this is where most of it comes from, is any electromagnetic energy. Visible light is just a little bitty part of that spectrum. Now, the book, I think, has a very nice picture of your spectrum. And I don't think the slide set shows that. Okay? So let me hold this up for those that don't have the book so you can see. That's fair. Okay? Very, very high energy rays that are out there in space, anywhere there's been nuclear reactions going on, gamma rays are hitting like crazy. Okay? Those are deadly. Okay? If you were to be exposed to them, you probably won't last too long. The longer you last, the more brutal it is. I mean, they kill tissue. And if they do it slowly, you're in pretty sad shape. Have y'all been hearing about that was a different kind. Get into too much there. Okay, then there's X-rays. Very high energy radiation. Now, we control X-rays. We use them to measure broken bones to see if your shoe fits, to see if your teeth are okay. We use X-rays in very, very small dosages. Now, have you ever noticed when you're having an X-ray, you have had some of you, right? Either in the mouth or a foot or leg or something, you've had them. Where do the technicians go when you're having the X-ray? Or the dentist? Yes, in another room, looking through a very dark piece of glass. And that wall, I guarantee you, has a bunch of lead between them and you, because they can't be exposed to it. You're just getting a little shock for a short time. They're in there every day. So they get behind there so they don't build up their dosage. Otherwise, you have to hire new technicians pretty frequently. That's not, but it's true, okay? So X-rays are pretty powerful electromagnetic radiation. Then you have your ultraviolet rays. Now, ultraviolet rays also are pretty high energy rays that do cause damage to tissue. Can you think of some examples? Sunburn, exactly. It's the ultraviolet radiation coming from the sun that burns our skin, okay? And too much of that over too long a period of time, it creates skin cancers. I've already had one small one removed. I've got another one forming here. I put sunblock on it every day because it gets exposed to the sun, that turns into skin cancer. So it kills tissue. All right? Other things that happen, I've also had one cataract removed. Exposure to ultraviolet radiation hardens the lens, the cornea, that kind of stuff, and therefore, after a while, you can't see. And a lot of people living in tropical areas, the older people are almost always going to have cataracts because they don't have Ray-Bans and stuff like this to block the ultraviolet radiation. If you are going to buy sunglasses, be sure it says UV protected. It doesn't do any good if they're just dark glasses and makes it easier for you to see in the bright light. If they're not blocking the ultraviolet radiation, that's UV, ultraviolet radiation, you can still be damaging your eyes. And then, finally, we reach this little bitty spectrum here. This is the visible light spectrum. That's all that gets through. Our atmosphere, thank goodness, is up there blocking that gamma radiation because there's tons of it out there in space. I mean, that's the predominant thing. The gamma radiation, the X-rays, the high energy, lots of ultraviolet there. Our atmosphere filters most of that out, and only the visible light gets through. A little bit of UV, that's why we still get sunburns, we still get damage done to our corneas and other. Oh, by the way, the other thing, have you ever known some of the, y'all are too young to know, but you'll recognize them as you get older, who I call the sun worshipers, okay? They go out there and just lie in the sun as long as they can and as much as they can. They have great looking tans, right? Until they get older and they have really horrendous wrinkles, okay? Because that damages tissue, okay? You lose the elasticity of the tissue. We've known a few people who were great looking when they were young and they're prunes when they're old, okay? So you choose, okay? All right. So then you have the visible light spectrum. A very narrow band is what our atmosphere allows through. That's why we can live on this planet, okay? So we talk about other inhabitable planets and stuff. They've got to have, for us to live there, they have to have an atmosphere thick enough and composed of the right materials to block most of that radiation. Otherwise, we'd be dead. Now, on many levels, to me, about the most dangerous occupation you could have would be an astronaut that has to go out there and do spacewalks. Now, it seems like that would be a really fun thing to do, you know, float around and do things. But I don't know if you remember the Soyuz space station. It was a Soviet space station. We had a space station up there that for a while, and it crashed to Earth, and the Soviets had one up there that stayed there a bit longer. So for a long time, we were cooperating with them. And but they didn't have the shuttle technology that we did, and they sent unmanned cargo ships up there, and they remotely tried to guide them in and stuff like that to resupply the astronauts or cosmonauts that were on the space station. Well, one of them came in, unmanned cargo ship, came in too fast, too hard, and destroyed a few modules, okay? And then they had to rush and get into some very tiny little modules there and live in very cramped quarters. Already it was cramped, even more so, because their space station was damaged, and they couldn't ride back on that cargo ship. It was unmanned, and it wasn't designed to re-enter with people on board. So it brought their food and scientific equipment and stuff like this. So they were stuck there in very cramped quarters, and the Soviets were not really all that known for having luxurious quarters anyway, so they were even worse. So our space shuttle, which could go up and dock, you know, stuff, we went up and sent crews to help repair that. Now, you know that where the cargo ship hit that and damaged things, there was mangled metal, probably jagged metal, where things had broken and stuff. So our astronauts had to be out there. Now, what do the astronauts wear? Big, bulky spacesuits. Now, there's two reasons they wear those. One, there is no atmosphere out there, so they have to be pressurized. Okay? So the spaceship suit has to be pressurized. Other thing, it has to deflect. And you'll notice when they're silver, reflecting most of that harmful radiation away. Probably some lead as well as silver and aluminum in those fibers and stuff, so not that much gets through to the people. Now, they're pressurized. What do we mean by that? Are you under any pressure right now? I'm not talking about school pressure. Air pressure. Yeah, you are. How much? You probably know this whether you realize it or not. 14.7 pounds per square inch. What's a pound per square inch? PSI. Every one of us is under about 14.7 pounds per square inch. Now, if you think about a square inch is about the area of your two thumb joints. Here, that's about 1 square inch. Okay? And think of how many square inches are on your body. A whole lot of them. 14.7, almost 15 pounds for every square inch of your body. That's how much weight you're supporting. That's why we have bones. Otherwise we'd be puppets. Okay? So we have that. Now, why aren't we crushed? Because our bodies are exerting an equal force. In fact, a little bit greater force. And that's why we are able to withstand that. So we've got probably 15 and a half, or I'm just guessing, pounds per square inch pushing out on us. That's our body pressure. Okay? Now, my mom used to do this. She's dead now, but she used to do this when she was old. She would take the skin on her hand and pull up, and she could make a tent. Now, mine stays up a little while because hers stood up there for a long time. She was losing some of the pressure. She called it Turner pressure in her body. You could do that, and it probably just goes flat down in no time. But mine stays up a little bit longer than yours would. I'm losing that too. Okay? So we have the pressure inside our body. See, it goes right back. Okay? Now, just imagine you're up there in outer space, walking or floating around up there, trying to repair some of this really badly damaged metal structure that's there on the space station so that they can dock again and use other modules. If they were to have just a minor little rip to that spacesuit, because there's no pressure out there, 15 plus pounds of pressure per square inch of their body, there goes the blood, the gases, and everything else, probably through your eyes, your nose. If the radiation didn't kill you, that wouldn't have a chance, because that's going to kill you first. That's why I say that's one of the most dangerous occupations on the planet. One little error, and you could be spewing into space in no time. What's that? Oh, yeah, okay. But you're still spewing. Okay. that would be what mattered to me. Okay. Okay, I'm not spewing on this. Okay, right. Okay. But the other thing is, even if that didn't get you, the radiation would. You get exposed to that gamma radiation, X radiation, lots of it, you'd be fried in no time. Well, unfortunately, radiation takes time, and it's a pretty bad situation. Does the name Fukushima come to mind? What's related to that? Anyone remember? Something to do with a tidal wave, an earthquake, and a tidal wave. What What language does that sound like? Fukushima. Huh? Japanese. It was on the island of Japan, one of the islands, I think Honshu, one of the islands. And remember, it wasn't that many years ago that the earthquake happened just off the island. Huge tidal wave came in, and unfortunately, they had built a major nuclear power plant right on that fault line where the earthquake occurred. So the earthquake, but also the tidal wave, came in and wiped out the power to that station. The nuclear power plant. And when the power went off, there was nothing to regulate the plant anymore. And what?
It melted down.
Yes, it melted down. Almost as bad as Chernobyl had been in Ukraine when it was the Soviet Union, but not nearly the exposure that other people felt. The Japanese had built it far better than the Russians had, or the Soviets had. But it was still a extremely hazardous situation. Now, this wasn't coming from the sun, but it was that ultra gamma radiation and that kind of stuff. And I've got to hand it to the Japanese. Someone had to go in there and clean some stuff up. And that basically was a death sentence. And you know what? Some of the older men in the neighborhood who had retired from the plant many years ago, but they knew the plant, they said, don't send in these young guys, send us in. Because most of our life is spent. Send us in, we'll clean it up. If we die a few years earlier, that's no great loss. At least we're not got kids and things like this anymore. And they volunteered to go in and clean it up. Basically, knowing that was going to shorten their lives. And it could have been pretty brutal in doing that too. But anyway, let's get on down. The next band of radiation here is what we call infrared radiation. Now, there's some of that out in outer space probably too, but most of this is once the light comes into our atmosphere slows it down. It doesn't slow it down. It lengthens the wavelength, reducing the frequency, which decreases the energy. Now, what does that result in? It's happening right now in your automobile out there in the parking lot. If you were to go out there and open the door and jump in, what would you feel? Pretty hot. Why? Why would it be any hotter? You haven't lit a fire in there, have you? You haven't left something running. Why would it be hotter in your car than it would be outside your car? Okay, the light coming in loses just enough wavelength and frequency to lengthen up and become infrared radiation, which is basically heat. And we call that effect what? People who grow plants use it. Growing plants even in the wintertime.
The greenhouse.
Greenhouse effect, you got it. That's what makes your car heat up inside. The greenhouse effect. The glass lets the light in, but it lengthens the wavelength, decreasing frequency, dropping it down to infrared radiation. Then the infrared radiation doesn't have enough energy to make it back out again. So it stays in there and builds up. That's the greenhouse effect. And that's what, at least the theory is, and I believe it, is happening with our atmosphere. We've got more and more and more carbon dioxide in our atmosphere than we've ever had in the history of the planet. And carbon dioxide is one of the greenhouse gases. And those greenhouse gases trap a little more heat from that light that comes in and doesn't let it re-radiate back out. And that's why we have very slowly and very gradually global warming. And if you go back and check, I believe worldwide we have probably set new average temperatures for the planet, I'd say 5 times out of the last 9 years or something like that. Historically higher temperature. It may even be worse than that. That's what's happening. That's the theory of it. So that visible light is a very small part of the spectrum. Then below that you have the infrared, and then you have radio waves and all sorts of other waves. That's radio energy. Now, nuclear energy is the energy coming from the nucleus of an atom, okay? And the energy involved with the nucleus and nuclear reactions that go on. There's 2 types of nuclear energy that we are sort of familiar with. There's a type that's going on the sun right now, and it's been going on for the last 5 billion years or so, and we hope it's going to continue going on for at least another 5 billion years. I want time to check out, okay? That's one type of nuclear energy. The other kind is the kind that's happening at the nuclear power plants, and Hiroshima and Nagasaki happened there. North Korea is claimed to have had some. Anyone know the differences between those nuclear energies? They have 2 different names. Sort of similar, but not quite the same. That on the sun is called fusion reactions. And the ones in the nuclear power plants or the bombs and things like that, those are fission nuclear reactions. Now, what's the difference between those?
Separation.
Exactly. Which is which?
Fission separates.
Yes. And fusion is joined together. What's being separated or joined? Atoms. Which ones are separated? Which ones are joined? Okay. Basically, great, big, heavy, unstable atoms are separated, like uranium, plutonium, those kinds of things. You'll find those on the way end of your periodic table. There's uranium right there, there's plutonium there. They're huge, unstable, that's what makes them radioactive elements, okay? Whereas fusion that's going on the sun, that's usually hydrogen to helium. And then when a star uses all its hydrogen and starts collapsing and going through various things, then helium can fuse to go to carbon. And then carbon can fuse to go to heavier and heavier things until you get up to iron, and there it pretty much stops, okay? Until you have a supernova, and then you make the heavier atoms. So iron is the most prevalent element on any planet, okay, Earth included. Our whole core is predominantly iron. We just can't get to it. Sort of lucky because it's really hot, okay, as in molten, okay? But when you have a supernova, then all these heavier elements are formed. That's why they're at much lower prevalence in our makeup than the other. So nuclear energy is one of those 2, fission or fusion. We'll talk about some of that maybe a little bit later. Okay? Now, let's talk about energy conversion. I don't quite agree with this first statement, but I know what they're saying. Any form of energy can be converted into another form. The reason I have a little problem saying that, low-level heat is hard to convert into anything useful. Okay? That's where energy is wasted. Okay? Low-level heat. Now, have any of you ever heard of nanotechnology? Okay, that's taking some things like huge carbon, I want to say compounds, but they're really elemental compounds, and you can do some really incredible things with that. Extremely small things, and it can use some of that low-level heat to produce electricity. Okay, very small scale, but if you can harness that, that would be a really big breakthrough. Okay, but energy flows from one form to another in natural processes. Okay, just like we talked about. The nuclear energy on the sun, which is happening continuously, is sending out radiant energy into the universe. Our atmosphere blocks most of that, letting just a little bit of visible light come through. That visible light is what the leaves use to store chemical energy, and then later it becomes petroleum or coal, as in millennia later, it becomes petroleum coal that we can burn, or we eat the fruit of that, or burn the wood, or do various things like this, and those are all natural processes. Okay? Another, and this is much simpler, would be a pendulum. Whoops. So here's one. A bowling ball. Okay? Now, any of you ever gone bowling? Okay. What's one of the first things you do? You lift the ball. So you're providing work to lift the ball above the floor, right? What are you doing to this energy? Say again? Not yet. You're lifting it. Yeah, you're giving it gravitational potential energy by lifting it. Okay? And then you push it, which gives it kinetic energy, plus you lower it, and both of those give it kinetic energy as it rolls down the lane. So here you're doing work on the bowling ball, increasing its potential energy, gravitational potential energy, and then the combination of letting that fall and pushing on it, you're giving kinetic energy to the ball. And then the ball does work on the pins, increasing kinetic energy of the pins, or it decreases its kinetic energy over some distance. So you see, that's energy conversion right there. The starches and sugars that guy ate for lunch or supper, that's what gives him the energy to lift the ball and then push the ball, and changing the ball's gravitational potential energy to kinetic energy. The ball's kinetic energy does work on the pins and changes the kinetic energy of the pins. Those are all energy processes, energy conversions happening. Here's the pendulum. Okay. Now what's going on here? Where do you see pendulum? Where do you use them? Clocks. Grandfather clocks or grandmother clocks, okay? And what you typically do is raise the pendulum to some height, okay? In raising it, what are you doing to it? Doing work on it? Changing what kind of energy? Potential energy. It's gravitational potential energy. So you get it as high as you're going to do it. Now let's time out here. Before you do that, you determine what the lowest point is going to be. I call that the zero reference level. Okay? You could have it being the floor, the sea level, or something else like this. I don't care. But it makes sense to have that as low as that pendulum will go in the process of doing this deal. Okay? So have that be the zero reference level. Okay? You raise it above that, you're increasing its potential energy by that formula. What was it? Potential energy formula? mgh, that's it. The mass of the pendulum, the gravitational acceleration, the combination of those is the weight of the pendulum times the height that you raised it above its zero reference level. Doesn't matter the distance it went this way, it's the height above the zero reference level. Wherever you stop there, that now is at 100% is potential energy, gravitational potential energy, no kinetic energy because you're holding it at rest. As soon as you release it, what happens to its energies? Nothing, huh? It hangs there. I did not. Okay? What happens? Okay, it starts losing potential energy because the height is decreasing and gaining kinetic energy because it's speeding up. It started real slow, speeds up. At some point, halfway down here, it's lost half of its potential energy, but that's gained. That same part becomes kinetic energy. And down here at the bottom, the zero reference level, you have no more potential energy, all of its kinetic energy. So where will that pendulum be going the fastest? Right down there. What was the formula for kinetic energy? velocity squared, exactly. That's why it's fastest there because it has the greatest kinetic energy here. But does it stop there? No, because its velocity keeps it moving, its momentum keeps it moving, but it has to swing up here because it has a fixed length here. So it swings up here, and what happens then? Now the kinetic energy becomes potential energy as it moves upward until some point, and how far can it go? That level right there where it was 100% potential, it can't go any higher because it wouldn't have any kinetic energy left. Now what's the same throughout the whole passage here? The potential energy is changing constantly, the kinetic energy is changing constantly. What's the same? Yeah, the total amount of energy, and what kind of energy is the sum of kinetic and potential? Mechanical energy, that stays fixed. And they don't say what it is, but that's mechanical energy, okay? And that's what we're going to be doing in lab today, by the way. Speaking of which, yeah, we got some time. So I knew and there it is, the energy of the pendulum. I would be more specific here and call it mechanical energy of the pendulum is the sum of its kinetic and potential energy. And that I would put as GPE, not just PE, okay? But that is fixed. It's constant throughout the motion. As kinetic and potential are exchanging with each other, mechanical energy remains fixed. All right. Good deal. Any questions on that? Okay. Now, energy conservation. Okay. Now, this is where things get a little squirrely in the book. They have energy conversion here, which we kind of hit some, but we're going to have some more slides later. But there is one that comes out here from the pendulum. Let's go back to the pendulum and we'll do it. Okay. Up here, I was asking you this earlier, all of the energy is potential energy. And what is the formula for that? You gave it to me before. It took you. Is weight times height, is that what you said? Which is mgh. Yeah, mgh. Down here, no mgh because the height is 0, so all of it's kinetic energy. And what's that formula? 1/2 mv squared. Okay? Now, because this energy is the same as that energy, it's all potential up here, all kinetic down here, you can set those equal to each other and say 1/2 mv squared is equal to mgh. Now, what we are looking for is the velocity at the bottom, the maximum velocity it's going to have right there at the bottom. So what we can do is multiply both sides of the equation by 2. That'll wipe out the 2 here. Divide both sides of the equation by m, and that, oh my goodness, it wipes out both of the m's. So it doesn't matter how heavy the pendulum is at all, okay? It can be light, it can be strong. Okay. A lighter one's going to be more affected by air resistance and stuff like this, but you know, it really doesn't matter. The formulas hold. And that gives you v squared is equal to 2gh, and then to get the speed, we take a square root. So v is equal to the square root of 2gh. That's the maximum speed it's going to have. It doesn't depend on mass. It doesn't depend on anything but how high you took it at the beginning. That's all. Speed's going to be the same. So the length of the pendulum has something to do with it. And if you were studying that, that would be involved in the picture too. Okay? Because G is constant all over the surface of the Earth. Now, if you're out there in outer space, you're off the surface of the Earth, you don't get it. But we don't worry about pendulum up there. Okay? So we're here on the surface of the Earth, and this is your speed. Okay? You may or may not want to use that later. That's up to you. Okay. Now, like I said, in the slide set, they do energy conservation next, and then go back and talk about some other energy conversions. But since we do, in case I forget to do it, let's go on and do it now. Okay. Because I'm liable to forget it. Okay. Let's do examples 3.9 and 3.10. A 1 kilogram book. What's that a measure of? That's the mass of the book. That's about this big book, not your little thin ones, but the big one. That's about 1 kilogram. Okay? Falls from the height of 1.0 meters. And that what did they say that was? That's your height, the h. Okay? What is its velocity just as it hits the floor? We're looking for speed. This is the unknown here. How are we going to get that? Say that again. Yeah? And what was that? Okay. Help them out. Okay. So we know at the beginning, when it's 1 meter above the floor, all of its energy is gravitational potential energy. And how much is that? mgh, which would be 1.0 kilogram, that's the mass, times, well, you're leaving out the 9.8, what units? Meters per second squared, times the height, 1.0 meters. I can do the math on this one, I think, without a calculator. 9.8 joules, exactly. Kilogram meter squared per second squared. That would be joules. So that's how much energy it has at the beginning. How much does it have at the end? Same thing. Except at the end, what is that? That's all going to be kinetic energy. So at the end, and what's the formula for kinetic energy? 1/2 mass times velocity squared, or speed squared. Okay? So I'm going to change those joules back to, I wrote it down because you said it, but I'm going to change them back to, whoops, I'm going to try to change them back to the fundamental units. Okay? And what are the fundamental units you see up here? Kilogram meter squared per second squared. Okay? Now, first thing I'm going to do is I'm looking for speeds. Multiplied by 2. Okay, so that gives me mv squared is equal to 19.6 kilogram meter squared per second squared. Okay, because the 1/2 had and the 2 have no units associated with it. Then what are we going to do? By the mass. And the mass was 1.0 kilograms. Okay, so the m's go out. That takes the kilograms out of here. So you still have 19. So your velocity squared is equal to 19.6 meters squared per second squared. Okay? And then what are we going to do? I don't care what v squared is. I want to know what v is. So how do we get v out of that? Take a square root. So v is equal to, now most of the time when you take a square root of both sides, you say plus or minus. But you know in this one, I'm pretty sure that it's not going backwards. So we're only going to take the positive square root. Okay? And what would that be? Well, the square root of 19 is going to be between what two numbers? Exactly, because 4 squared is 16, 5 squared is 25, 19.6 is somewhere in between. So it's going to be between 4 and 5. So if you got a square root, you can look at it. I mean, if you got a calculator, you can do it, or do it, or you can look in the book and see what it is. They say 4.4, and they say it wrong in the book, or at least in my book it is. They say meters seconds. It's not. It's meters per second, because it's meters squared per second squared. You take the square root of the units as well as the number. Okay, 4.4 meters per second. Okay, now, Teff took me through that way, which is the way I usually do it too. But remember, we just came up with another formula. Remember, V is equal to the square root of 2GH. The mass doesn't even enter this. Let's see what happens then. The square root of 2 times 9.8 would be 19.6 times height of 1. So that's it. So yeah, we got the same thing. The units come out better this way. You have to fiddle with the units up there. But yeah, 4.4 meters per second. Second? Yeah, the meters cancel out. But in doing that, you lose the kilograms here, which you don't see in that formula there. But, it doesn't matter because they don't show on either side. You would have G, which is meters per second squared, times meters, so meters squared per second squared, second square root of a meter per second. So they work out fine, perfectly fine. And let me see, I didn't see you when you came in, Courtney, right? Okay. Glad to catch you. Okay. Anyone else come in since I called roll that I may have missed? Okay. Now, let's do example 310. Now, what we're going to do here, it says, what is the kinetic energy of the 1 kilogram book just before it hits the floor after that 1 meter fall? What's its kinetic energy? Yes, you're absolutely right. Here was the gravitational potential energy, 9.8 joules. It better be 9.8 joules. But you know what they do in the book? They take you through this and get the 4.4, which is a round off. If you place that in the calculator and take the square root of that, it's rounding off. It round off. Then you go back and square it and multiply by the mass and 1/2. You come out with a different number, and the one they say in the book is 9.7 joules. 9.7 joules. Now, they didn't come up with that because they thought it might have lost a tenth of a joule in air resistance. They came up with it because they had a round-off error there. So there's no reason to go back through and multiply that, square it, and multiply it by the mass and take half of it. You just look at this and say, this was kinetic, the mechanical energy at the top, that's going to be the kinetic energy at the bottom. 9.8, not 9.7. So sometimes they're rounding off, bites them, okay? In the foot, let's say, or somewhere else. Okay. So there's energy conversion. Okay. So let's move to energy conservation. We'll come back and do energy. I'm sorry, I said that was energy. Oh, I was right. We've already done energy conversion. We'll do energy conservation now. Here is a statement that is indeed always true. Energy is never created nor destroyed. You can't. You can't create energy. You can't destroy energy. You can make it change its forms from a not so useful form to a useful form. Like petroleum sitting there, you can catch it on fire and it can burn up your building. That's not very useful. But take that same petroleum and in a controlled environment, your pistons and things like that, it can do some very useful work. Okay? But you can't create nor destroy the energy. It's already there. Stored chemical energy that a long time ago was nuclear energy, became radiant energy, became stored chemical energy, and then changed several times. Energy can be converted from one form to another, but the total energy remains constant. The trouble is it can change form so fast and so furiously you can't keep up with it. Seems like you're creating energy, but you're not. Okay? One example of this is free fall. Okay? I've already given this example several times. You throw a ball into the air. Once it leaves your hand, it's in free fall. Even though it's going up and not falling, it is being influenced by gravity. And as long as you ignore air resistance, gravity alone. Okay? Now, there are other transfer mechanisms. You did work on the ball to get it up there, or heat, which usually comes through friction. Okay? But it may not. It may come from blowing up fuel in your head of your piston. And that heat is then going to be doing work and converting energy. Okay? And this is what we were just saying. When you throw the ball into the air, the potential energy, gravitational potential energy you're losing is the kinetic energy you're gaining. That's when you drop it from rest, and all it has is potential energy, gravitational potential energy. You release it, it starts losing gravitational potential, picking up kinetic as it goes. And here's that formula we just did. mgh is equal to 1/2 mv squared. This is the final velocity. This is the maximum height above when it was at rest. And this is at the bottom when it has no more potential energy. You solve for VL, so why didn't they write it the other way? The m's go out, the 2 gets multiplied here, so 2gh, square root of that is your V. Same thing we just used and talked about earlier. Okay? Now, here is another example of the free fall. If you started 10 meters up, now what's 10 meters? It's about a 3-story building. Okay? So let's say we're on the highest part of the building, up on the roof there, about 10 meters above the ground, and you drop the ball. Drop it. Don't throw it. Drop it. Okay? Don't throw it upward. Drop it. Okay? So its initial velocity is 0, so it has 0 kinetic energy. You're releasing it from rest. Okay? The velocity is 0 at that point. All its energy is gravitational potential energy, mgh. Mass is 10. No, wait, what's the ball? I guess it's 1 kilogram. Yeah, 1 kilogram mass. G was 9.8. The height is 10 meters. So that would be 98 joules. Halfway down at 5 meters, now its potential energy is mg times 5, which would be exactly half that energy, 49 joules. Because of that, you know its kinetic energy has to be the other 49 joules. So they have this order out of place. Once you know that 49 joules, you can use this formula to get your velocity. Okay? Your height, well, the height was 5 meters here. 2 times g times 5, square root of that will give you exactly 9.9 meters per second. So halfway down, it's picked up 9.9 meters per second velocity. Started off at 0. When it reaches the bottom, you think the velocity will be the same, greater, or less? Doubled, or what? If you were going by time, it would be double. Half the time, it would be. But it's not half the time. There it was going more slowly. It's at a higher speed now, so it's going faster. So it doesn't have the time that it reaches the bottom. It's going to be much less time. So the velocity is actually less than twice that. Okay? But you can still get that from here. Square root of 2g. Okay, that's your velocity. The h is 0. Oh, wait, you can't really do it that way either. What you have to do is, this is the height from the very top. That's right. Okay. Yeah, you're measuring your height from the top. Here your height would be 0. How far it's fallen would be 0, so that's why this is 0. There would be 5, here would be 10. The square root of 2g times 10. And that would give you your 14 meters per second. But all your kinetic energy is all the initial energy you had at the top was potential. Now all of it is kinetic at the bottom, 14 meters per second. Now, question for you. What never changes in that activity there? Mechanical energy never changes. It's always 9.8. 98 plus 0 is 98. 49 plus 49 is 98. 0 plus 98 is 98. Everywhere in between. 98 joules. Okay. mechanical energy is conserved. Now we're looking at flow of energy, which we started off and they had the thing, energy flow was the title of 3.3. Now we're looking again at energy flow. And this is just another example of what we've said several times. Energy is never created nor destroyed. Conservation of energy, total energy. Energy can be converted from one form to another, but the total energy remains constant. They said that before. And here's an example of this. The nuclear energy in the sun is producing enormous amounts of energy constantly, okay? Going out in every direction around it. That little bit that hits our planet filters through our atmosphere, so the harmful stuff doesn't make it in. Only that little visible spectrum does make it in. That becomes radiant energy. That's radiant energy as soon as it leaves the sun. Once it was nuclear, but now that little bit comes through, hits the little green tree, leaves on the tree, and let's just say that's a pecan tree. I like pecans, you know, and that's storing that energy in the oil in the pecan. We eat the pecans, that gives us energy, then we can pedal the bicycle and also do some sweating. Okay, so we're heating up, the bicycle's heating up here as it goes. We've got mechanical energy, the energy of motion, kinetic energy. But when you pressed on the brakes on the bicycle, what was produced? Heat, exactly. I know y'all have experienced that before, pulling off a tire, and if you happen to touch the brakes shortly after they brought it in, you're going to burn yourself, right? So you have to be very careful of that. When you put on the brakes, that stops it by friction, heat, and it goes back as radiant energy. This time, infrared energy back into the atmosphere. Okay? Circle of life, right? Now, energy sources today. I don't think we're going to have time for this, so we will pick up there next time. Okay? Now that means two things. Number one, the beginning of next class will be finishing this chapter. Okay? That means there won't be a test on this chapter on Thursday. It'll be next Tuesday. Okay? Now, the other thing it means, we've got to finish this part, the first part of the class, and then move into chapter 4. If we get enough covered in chapter 4, then we can have a lab, the first lab in chapter 4 next time. Otherwise, it may be a long class. Okay? So let's hope we can get far enough along to have the first lab in chapter 4. I think we can. I'll try to move it along and finish this early next week. Okay, then we'll have a lab in chapter 4, and then we'll finish chapter 3, start in chapter 4, hopefully get far enough for a lab, then have the lab in chapter 4, first lab in chapter 4. Then the next day, that'll be Tuesday of next week, we will continue in chapter 4, have the second lab in 4, I think we'll get far enough for that, but stop 30 minutes early so that you have time to do the test in chapter 3. Okay? Make sense? All right. We will go from there. So let me end this. And before you go anywhere, let me go on and pass out the labs to you. This is one that I made up. Not made, I got it from other sources. But it's not the long multi-page thing like we have had. And by the way, folks, since I got a little bit of time, don't have a lot, let me just go over a thing. Number 1, research papers. I've received one only, okay? Out of, what is this, 23 people in the class or something like that? One out of that, not the best percentage, okay? We only have less than a month left in the term. Please get your papers done. I thought I was going to have a swarm of them coming in after spring break. Didn't happen, see, so far. Okay, so get your papers in. Lab 1, There's one person hasn't turned in lab 1. I need your lab 1. Okay? Test 1. Hey, the last person who needed to take it took it last week, at the end of last week, so I can return your test 1 to you. Okay? Let me do that right now. Okay? So my load will be a little bit lighter. Okay? All right, here's your test 1. Number. Haley. Josh. Alexis. Darrell. Justin. Matt. Travis. Shanika just went to her other class. So when she comes into lab, get that one cold. Brandon. Gary just made it in today. Yeah.
What's up?
Yeah, goodness gracious. Okay, Joseph. Right? CP. I mean, Coco. Hannah. Will. Miranda. Brothers. And all right. Good deal. Okay, glad y'all got those in. Okay. Lab 2. 1, 2. People haven't turned in lab 2. Lab 3. 1, 2, 3, 4, 5 people haven't turned in lab 3. And it's not always the same people, by the way, too. Lab 4. 1 person hasn't turned in lab 4. Test 2. 1, 2, 3 people haven't done test 2. And lab 5, 1, 2, 3, 4, 5 people haven't turned in lab 5. And we're going to do lab 6 today. So I'm glad at least everybody, and the last person did it Thursday, I think it was, so I didn't have it graded in time. So let me but please get those labs in so I can get rid of these labs. You're that heavy to carry around. Okay. And let's see, Coco needed the last 2 labs or just the last lab?
I need the last 2.
Okay. While I'm here, let me get these. Okay, laws of motion. Goodness, I'm about to lose load here. All right. Okay. And working power. Okay. And that's how we need to start. I'm not sure you turned it in. Well, I'll check. I thought I remembered not seeing your name. The grade value. Okay, you got the working power though, right?
And I checked my test Thursday.
Yeah, you can. You want to come in early and take it, or? Okay. I'm free from 11:15 until class time at 1:15. Okay. All right. Now I went through all that and still haven't handed out the rest of it. That's what I was in the process of doing. Here we go. And unfortunately, this is one that I did, so it turned out being a little on the short side, as in a single page. Down. That's one down. That's two down. Three down. Four down. Four down. One down. Okay. Now we'll be going back down to 259. Okay. Let me put this on the board because I'm afraid we may have lost somebody last time. I don't know. I thought I said it this time, but so it'll take me just a little while to get down there, but I'll try to get there as soon as I can. That's not much better. This don't go on well. That's worse. That's almost gone. That's the home. Goodness gracious. See if this will work.
Do we just turn our research on?
You can turn it into me?
Yes. That's just the topic.
Yes.
Does that work?
Yes.
Okay.
Okay. All right, it'll take me just a few minutes to get all my stuff down there, but we'll be ready to go fairly soon. I'm going. Yeah, there's still some more coming. How many more coming? Is that all? Okay. So we'll need 10 on each team. Let me just count here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. You'll be on this team. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Got it. Okay. Now, we have two pendula here. They're not on rigid, they're on strings, but it still works. Okay? Now, each of these masses down here, you can read it and see, 500 grams. Okay? 500 grams. Okay? But what I want you to do is record that mass in kilograms. So how many kilograms is 500 grams? It is exactly half, so 0.5 grams, 5 kilograms, 0.5 kilograms. Okay. Now, someone from each of the teams, what you're to do is measure from the floor to the bottom, because the bottom's sort of flat, the bottom of that mass, okay, to the nearest tenth of a centimeter. But you're going to record that in meters. Okay, so it'll be so many. Same here, from the floor to the bottom of that, the flat level bottom, to the nearest tenth of a centimeter, but you record it in meters. So yeah, do it and tell me what you get. Okay? Somebody from each team. Don't be shy. Okay, this thing's getting way ahead. From the floor to the bottom of the thing. What do you get?
42.
Okay, and that was centimeters. And how many meters will that be? Huh? Yeah, exactly. What do you get?
Point
Okay,
42.
and how many meters will that be? Very good.
Point 42.
Okay. Now, I don't know that everybody can do this because we're packed in here, but you can look at me and imagine doing it from here too. I'm putting this at the end of the meter stick with the string taut here, and how high is it above the floor now? Okay, so what's your difference in height from what it was there to here?
So you do 1 meter minus
What you just recorded, exactly. Okay, pretty easy to do, right? That will be in meters. And as soon as you got it, let me know what you got so I can tell you whether it's reasonable or not.
58.
That sounds good. What y'all get?
50.
What y'all get?
0.77.
Sounds good. Sounds good. Okay. Now, with your numbers that you just had, even though I'll be demonstrating this to just one of them, with the numbers you just had, the next question here is calculate the gravitational potential energy of this mass at this level. What is that formula? Okay. And what's weight?
0.5 kilograms.
That's not a weight.
Mass times zero, or mass.
Yeah, mass times the acceleration due to gravity. So it's the mass times g times whatever your change of height was, the delta h. You had different delta h's, so you do the calculation. I hope somebody, at least one person on each team, has a calculator. Do they? Okay, yeah. At least one there. At least one over here. Okay. What would be the units? Everybody got an answer?
What's the height?
Huh?
M
M
times
G
D
times the delta H.
times this.
Remember, we're always more interested in the change of potential energy than the actual amount of it. So there's going to be zero left.
The height will be like right there with you.
Okay. The change of height from down there to up here.
2.842.
Say it again.
2.842.
That sounds reasonable. What y'all get? Okay. And what units?
Let's put 2.8 joules.
Joules. Exactly. Is that what you got to? Somebody else? Yep. Compared to somebody else.
I don't remember 2.8.
Oh, you got one calculator in the group? You did. Oh, okay. You get it? Yep. All right. Okay. Now, next question. Next question is, while it's sitting up here on top of the meter stick, what is the velocity here at the top? Zero. It's not moving. Okay? And then, with your enhanced mathematical skills, what's the kinetic energy at the top?
0.
Oh, very good. Y'all are quick. Okay? Do that calculation real quickly. What's the mechanical energy here at the top?
0.
Oh, really? What is that? Yes, it's the sum of the gravitational potential energy plus kinetic energy. So whatever yours was, yours is different from theirs, so don't listen to Will. He'll lead you astray. Okay? Never mind. Okay. Now, I will need some room here, so don't let me break the kneecap, okay? Especially if it's not mine. Okay. Now, when I release this, whoa, always all things fall apart. Okay. What did you notice happened there besides the banging things and falling things off? Okay. It started at zero kinetic energy, zero velocity here, and when I released it, okay, it picked up speed till it went to the bottom and then started losing speed. About how far did it go over there? Approximately. About the same distance. And notice when it comes back here, if it doesn't hit anything. Okay. Yeah. Well, we'll worry about that later. We'll do it on this one, okay? But it would come back about the same. So, where was its maximum speed? At the bottom. So let's talk about the bottom now. What would you predict the mechanical energy at the bottom to be?
It would be
0.
It would be the same as the potential.
Yes, mechanical energy does not change. So whatever it was at the top, same at the bottom, right? Okay. What's the GPE at the bottom? Gravitational potential energy at the bottom.
0.
Yes, y'all been saying 0 for the last 3 answers. You finally got one. Okay. What is the kinetic energy at the bottom? Oh, really? So, yes. All of the mechanical energy is now kinetic energy. Okay. Now, what is the velocity at the bottom? Oh, really? What units? Okay, velocity measured in joules, huh? Oh boy, new physics happening today, every day. Okay. No, how are we going to figure out what the velocity at the bottom is?
No, that's another.
Okay. Do you want to go out to the classroom where I got a board and I was
Square root.
okay? What was it? Okay. How does that go?
Square root 2hg.
That's it. And the h is your delta h that we did on number 3. And the g is the same g you used before, so it's the square root of 2g delta h. So you'll need a calculator to do it. Okay? Did you do it on there? Or did you do it there? Oh, yeah. On this one, yeah, you have to put in the numbers and then hit square root. Hey! Only one messing with my balls here.
Somebody knows something.
Have y'all got velocities yet? Working on it. You got one? Yeah. You got an answer yet? Anybody? Huh?
3.4.
Okay, you use, 3.4, what unit?
Meters per second.
Meters per second. Okay. Now, is that what you got there? I'd like to have verification with somebody else. What y'all get?
Velocity bottom.
What'd you say, Justin? 1.35?
Second? 2.40 meters per second. Okay, you were doing this one. Okay. What did y'all get?
8.4.
Okay, something's a little off because this one would not be going as fast as that one. Yeah, this should be the faster one. So one of you is off. I don't know which one. How did y'all do yours? Okay, wait. This is the mechanical energy. Okay, now, take me through how do you do it again? What formula do you use? This is neither H nor G nor G. Okay, there's your H. And G. That's arrows on your shirt. Yeah, acceleration due to gravity, which is 9.8. So 2 times that, and then take it. Okay, and you got,
3.4.
yeah, those sound reasonable. Okay, what units? Really? Working every time so far, so why not go for it again? What's velocity measured in? Meters per second. Yeah, something like that. All right. Now that finishes the first part of the lab. Now we're going to go to another part. I need somebody over here manning a meter stick, and somebody over here manning a meter stick. Okay. Okay, good. All right, get further back a little bit. And what I want you to do is put this on the top of your meter stick when it's on the floor. That would be fine by you to do like this. That way it's easier to hold. Okay. Now, okay, keep the string taut. Okay, you get a little closer here. Now, what I want you to do, the old man's going to get down here. Oh, man. Okay. Now, I'm not sure. Getting up well. Okay. Okay. Now, what I want you to do is release yours, and you estimate how high it goes over here. All you do is release it. You see about how high it goes here. Okay. Do it from the top of it. You lowered it some and then released it. About the same. About a meter. Okay, grab it again. Okay. Now this time, are y'all paying attention?
Yes.
Okay. This time I'm going to peg it about a third of the way down, and I want y'all to estimate how high it goes on the meter stick over here. So anytime you want to let go, you can. About the same. About a meter. That is an answer on your sheet, right?
6.
Okay. Okay. Next, about a third of the way down, it goes to about a meter. Yeah. Okay. Everybody got it? Got it?
Yeah.
About a meter. That's number 6. By the way, Roman numeral 1, answer any 10 questions. You can ignore that because that was from a different book and everything. So don't worry about it. Okay? All right, we're going to do it again. So I'll do it again. This time I'm going to peg it about halfway down. So I want you to do the same thing. See about, flip it around so you do the meter side. Yeah, okay. See about how high it goes when me pegging about halfway down. About the same, about a meter. So you can answer that one. For number 8, that was number 7. Number 6 was about a meter. Number 7 was about a meter. You got it? Okay. Without destroying the rest of the lab here. Okay. Everybody got it? All right. Now I'm going to peg it about 2/3 of the way down. Okay. Keep the string taut. Okay. Peg it about 2/3 of the way down. And see what happens. Oh! What happens at that point? Answer it. Wrapped around the peg. That's the first part. Wrapped around the peg. That's the first part. The second part is why. It had momentum every other time.
But you had a thing around it. So the made it go around it since you understand it.
Okay. What are you saying there now? You may be right on the money. I just not following. Okay. Well, my peg was lower. Okay. Now, let's think about it. Why did it go back to a meter every time before that? Why did it stop at a meter? Why didn't it go further than a meter?
It's the same amount of energy.
Because what?
The same amount of energy.
Okay, and it all went to potential energy. And when it got to all the kinetic energy became potential energy, that was about at a meter, right? But when I peg it way down here, there's not enough string for it to get back to the top, was there? So since it couldn't get back to a meter, it couldn't lose all of its kinetic energy to potential energy. So since it still had kinetic energy, it kept going. It wrapped around the peg. Does that make sense? Because when I pegged 2/3 of the way down, it did not have enough string to get back to 1 meter. So it couldn't lose all of its kinetic energy to potential energy, and therefore it wrapped around the peg. Okay? However you want to do it, I can take this if you like. And what we can do is move back to the laboratory. That was part 2. We'll go back to the thing and do part 3. Okay, we haven't done number 9 yet. We'll get to that. I was just getting people out of here. So
It's gotta be number 9. He's still big. Oh my gosh. Look at your person.
you got it? All right. Now, the last question 9 we didn't answer there just because people didn't have much room to write. So what is that? Number 9. What conservation principle does this experiment demonstrate? Next Okay. Now, all the ones that were on the team over here, whose minimum displacement was 0.23 meters, okay? The ones on this side, in your margin here, you write by number 2, 0.23 meters. All the ones that were on this team, the one over here, you write in the margin 0.42 meters. Okay, and then go through and do the same calculations you did with your measurement with the other team's measurement. And most of these you can do in the margin. These are number 4 and 5, right either above or below the line, wherever you can find room to write. Answer all the questions. Yeah. All the questions. 2, 3, 4, and 5. Okay? Do all those calculations, 2, 3, 4, and 5, for the other teams. No, hey, okay. And be sure you do the calculations. You don't just copy someone's calculations. Okay, does anyone have any questions, or can I go on and shut down and start uploading the program? No questions?